Welcome to this talk. I am Alexandre Celma-Miralles, and I will present a pilot study entitled Neural Entrainment to an Ambiguous Polyrhythm with Distinct Metrical Context. This study was run together with Cecilie Møller, Jan Stupacher, and Peter Vuust in the Center for Music in the Brain at Aarhus University. Imagine Corona is over and we go back to dance floors. After listening to the music for a few seconds, we start moving our body following some periodicities. The more salient periodicity is the beat, which can be grouped or subdivided in slower or faster periodicities, building a hierarchical metrical structure. This metrical structure establishes referential temporal points in the rhythms of music. In music, we can find rhythms with overlapping metrical structures. This is the case of polyrhythms, in which more than one regular stream occurs at the same time. For instance, the 3/4 polyrhythm combines a ternary and a quaternary pulse train, which creates an ambiguous percept. Here, we used the 3/4 polyrhythm to study how metrical contexts modify the perception of one over the other pulse train, observing the amplitudes of the frequency tagging steady-state evoked potentials. In our stimuli, we presented the 3 pulse train at 90 beats per minute and the 4 pulse train at 120 beats per minute. We created 3 stimuli: the polyrhythm alone, a version in which a ternary metrical framework precedes the polyrhythm, and a version in which a quaternary metrical framework precedes the polyrhythm. We tested 16 participants with our paradigm, which includes 3 blocks. First, there is the spontaneous beat perception, in which participants listen to 7 trials of the polyrhythm alone. Then, they listen to 14 trials introduced with the 2 metrical frameworks presented in random order. Finally, each participant had to tap to the perceived beat of the polyrhythm 3 times in a short behavioral block. We recorded the tapping responses to check that the stimuli was perceptually ambiguous. We found that more or less half of the participants tapped the slow meter and the other half the fast meter. Almost no participants tapped a binary meter or an unclear rhythm. Furthermore, participants' meter was quite stable across the 3 trials. To study neural entrainment, we recorded the EEG of the participants with 32 electrodes. We averaged the trials related to the same stimulus and computed the mean of frontocentral electrodes. Then, we converted the steady-state evoked potentials into frequency amplitudes following Noetharadan's frequency tagging methods. This allowed us to observe peaks related to the frequency of the beat, metrical groupings, and harmonics or subdivisions. Here we can see the frequency amplitudes of the participants listening to the polyrhythm. In blue, the peak for the quaternary beat at 2 Hz, and in red, the peak for the ternary beat at 1.5 Hz. We can compare how these peaks change in relation to the peaks from the envelope of the auditory stimulus. Notice that the peaks at 1, 4, and 6 Hz seem to change in the EEG frequency spectrum. Also notice that the quaternary peak is higher because we had to increase the amplitude of the 4 pulse train to compensate for the general tendency of tapping the 3 pulse train. If you are interested in this bias, see the posters by Jan and Cecilie. Here we can see the frequency amplitudes of the participants listening to the polyrhythm preceded by metrical context. In red, the ternary metrical framework, and in blue, the quaternary metrical framework. You can see some differences in the peaks at 1.5 Hz, the ternary meter, or 1 Hz, the binary meter. These differences are also found in the frequency spectrum of the participants listening to the metrical frameworks. As you can see, there are distinctive peaks at the frequencies related to each meter. We used the repeated measures ANOVA to compare the neural amplitudes across the three conditions, but we couldn't find any significant effect related to the metrical framework. The only significant finding was that the peak at 2 Hz, the quaternary meter, was higher than the other peaks. We found similar results when we included the group factor in the ANOVA, taking into account participants that tapped ternary, quaternary, or unclear meters. There was no distinction between tappers. Note that the tapping data was to verify the perceptual ambiguity of our stimuli and doesn't necessarily indicate that an individual perceived this bit in the EEG experiment. To determine which frequencies stood out in relation to the others, we normalized our 7 frequencies of interest using z-scores, similar as Nosarad and colleagues 2012. These frequencies were related to the full polyrhythm, the binary meter, the ternary meter, the first harmonic of the ternary meter, the first harmonic of the quaternary meter, and the first common harmonic of both meters. This normalization was applied to the stimulus envelope as well as the EEG of each participant. Here we show the normalized peaks of the stimulus envelope, the black stars, and the normalized peaks of the EEG after the ternary and the quaternary metrical framework, red for the ternary and blue for the quaternary. One sample t-test revealed that, compared to the stimulus envelope, normalized neural peak amplitudes were selectively enhanced at 0.5, 1.5, and 3 Hz for ternary framework, and at 1 Hz for the quaternary framework. The asterisks mark Bonferroni corrected significance. Let's turn to the results and discussion. We didn't find differences directly in the neural amplitudes across conditions, perhaps due to the variability among participants, or maybe because of little statistical power. However, compared to the frequency peaks of the sound envelope, metrical context enhanced neural amplitudes at meter-related frequencies, especially in the ternary framework highlighting the 3-pulse strain. Remember that, to compensate the natural tendency to tap the 3-pulse strain in the 3/4 polyrhythm, we had to increase the volume of the 4-pulse strain. This made the neural peak amplitudes difficult to compare. To know more on this tapping bias, read our preprint in bioRxiv or check the posters by Jan and Cecilie. Before ending, I would like to highlight that this study is a pilot with several limitations that can be improved. First, the tapping responses only aimed to verify the presence of 3 and 4-bit perceivers. However, the tapping responses may be altered by the metrical context presented during the EEG recordings. In the future, we should record a baseline tapping of the 3/4 polyrhythm previous to any EEG recording. Second, here we cannot directly link selective enhancement of neural amplitudes to tapping responses. To do so, we should record participants' tapping responses after the presentation of each stimulus. Finally, the quaternary auditory framework contained an instrument playing at the binary meter. In the future, we should design a stimulus that uniquely emphasizes the quaternary meter. To end up, I would like to thank you all for your attention, and also thanks to the institutional funding that supported this research. Now, there is time for your questions.